And now on to Waveguide. I've just alluded to Waveguide, and I wanted to show you the different forms of it when we want to connect the different parts of the transmitter. Here is, this is a 6-inch rule. And if you remember, this is about a half a wavelength, and this is a lot less than a quarter. Here's an L-band rectangular waveguide. Here we have its C-band, and E field and an H field bends, so that you can, you can bend whether the field is in this direction or that direction. You can bend it 90 degrees. We can apply a twist of 90 degrees with this kind of a waveguide. And then we have where we go from an X-band coax, we can go out to a waveguide adapter through this kind of a device. And the whole issue with these is, what are the losses? And the thing I want to point out is the least loss, obviously, per unit length would be, at a given frequency, would be just be a straight waveguide. And whenever you have a connections, there's a very fraction of a dB of loss whenever you have one of these connections. Here is an X-band flexible waveguide and an S-band flexible waveguide, and you can see the ridging on the inside of the S-band flexible waveguide, which allows you to, with your hand, but with incurred extra losses, the waveguide, you can if one was at one height and another had to be at a different one, you can put them in at various by hand, as in this C-band flexible waveguide. And Carbon Sensor Systems supplied me. We went down with one of the directors and just took a whole bunch of these different waveguide pieces, and we just took pictures of them, and they were kind enough. You notice in this waveguide we have a ridge, and the ridge can be added to the waveguide. It increases the bandwidth of operation, but again, you have a wider band operation, but you're going to pay for it. There'll be at certain frequencies, you'll be maximum loss. You pay for everything. And here's a waveguide at C-band without ridges. Each waveguide has a cutoff wavelength of frequency, and that is a frequency beyond which you can't support modes. And the lowest active mode you can have would be a T10 or a T01 in a rectangular waveguide. And this is a C-band flexible waveguide where A is the life, and it's approximately half a wavelength long. And you can see from the geometry, it's approximately, it's less than a quarter is the B dimension. And you can calculate the cutoff frequency just by this formula. And I believe there's a little section in ULAB and in any waveguide book as to how you can calculate these. And usually these systems work in a T10 mode. And here's a directional coupler at X-band. And here's the magic T, which I referred to you when we went over in the monopulse section, how this is used to generate the sum and the difference signal from two input signals. And it's ridged so you can have wider bandwidth with it. But as I believe, it doesn't have, well, for this to work, this C-band ridged magic T to work, you have to have the 90-degree angles so it wouldn't be flexible. Here's what a rotary joint looks like. If you have a transmitter, it's going to be putting a signal in, and if you have an antenna that's rotating around, you have to have a joint that's flexible. and it couples microwave energy from the transmitter to the antenna feed as the antenna rotates. And again, there'll be a loss in here. And it's located in the base of the antenna, which rotates about the vertical axis. The easiest way to look up all these losses, and that's what we always do when we're generating the losses between the transmitter and the receiver, is you can go online and for any frequency, or you can look at columns. Oh, this picture was from Mega RF Solutions. You can look up and they'll tell you just what the losses are for this model rotary joint at this frequency. Now I'm going to look into other ways of transmitting that are on a much smaller scale. And these are used in microwave integrated circuitry. And this is the first level now in looking down at how we make very small transmitters and receivers altogether small. I showed you some pictures of some TR modules, and we looked a bit at architectures. Later on in the last lecture, we're going to show you architectures, but I wanted to show you just the basic strip line transmission line and how it works. What we have is a ground plane, and a strip line is a planar form of transmission line. This is a planar form. And we have a ground plane right here, and there's a dielectric between it, and that's the epsilon that characterizes it, and it has a thickness, D. And halfway through it is a conductor of width W, which is etched onto and then covered with an equal thickness of dielectric and another ground plane. And here is a side view showing the electric fields from end on. Here is the conductor, and the electric fields, you know, always leave a conductor perpendicularly, and then around it are the magnetic fields. And microwave strip line normally operates with a transverse electric and magnetic mode. That's where the magnetic field and the electric field are perpendicular to the axis of propagation. And here you see a microstrip transmission line, which is slightly different, a form of planar transmission line, and it can be fabricated with lithographic processes, and by that they're much smaller. And integration of passive and active microwave devices is straightforward with microstrip transmission line between the devices on photolithographic plane. The conductor here is of width W, is printed, not placed. It's printed on a dielectric substrate of thickness D, and the substrate is grounded. And the mode of transmission is a hybrid TM-TE wave. And since the substrate thickness is very thin, a lambda is much greater than D, though, the TEM mode of propagation is a reasonable approximation to reality. And here's how the electric and magnetic field lines go for that microstrip transmission line. Now, comparing the different types of waveguide or transmission lines, in coax, the preferred mode is a TEM mode, and in waveguide, it's a TE10, and strip line, it's TEM, and we saw it for microstrip. The preferred mode is a quasi-TEM mode. The bandwidth is very high in strip line, microstrip, and coax, but it's low in waveguides because of the rigid size of it. In physical size, though, coax is large, waveguide is also large, and strip line is moderate, and microstrip is very small. In terms of power capacity, you've got moderate capacity and power With coax, with waveguide, you have very high power capacity and quite low for strip line and microstrip. And the losses are moderate with coax, they're quite low with waveguide, and they're high with strip line, but the strip line is very small, and so that it's sort of loss per unit length. The ease in fabrication is moderate for the first two and easy for the second two. And the intercomponent integration is hard with these. You have to worry about the losses, and I'll show you the examples of I think I showed you one of the complex monopulse feed with one waveguide network earlier. And they're moderate with strip line, and they're very easy with a microstrip. First of all here, before we get into the next phase, here's to show you some examples. Here's an X-band slotted waveguide antenna. The slotted waveguide antenna produces a pencil beam, and it's mechanically scanned in azimuth and elevation. And what you have in the back here is a microwave joint, and the energy goes into this waveguide, where it's fed internally down the lines, and energy transmits out in this offset waveguide slots. And this type of an antenna is in the nose of most commercial airborne weather radars. The commercial, and it's an X-band, I believe, the antenna is about this round when I took a picture of it. This was down at Cobham Systems, and so you could count off, and you get the lambda over 2s here where you have the slots, and to figure out the wavelength that this radar works at, and you can see that the slots are offset and in certain phases so that they give a pencil beam, and then behind this beam will be a gimbal which will move the antenna around. And now to microwave integrated circuitry. Microwave integrated circuitry, which has the acronym MIC, this technology is just digital circuitry that's moved to technology that's smaller, lighter, more integrated than solid-state microwave circuitry. Hybrid microwave integrated circuitry have the common substrates used are alumina, quartz, and Teflon fiber, and computer-aided design tools are used for fabrication, where your substrate is covered with metal, then etched to remove the area of unwanted metal, and then solder or wire bonding is used to implant discrete devices like resistors or capacitors or amplifiers. Monolithic MIC, or MMICs as it's called, is more recent technology than the hybrid MIC technology. And semiconductors such as gallium arsenide are often used as the substrate. The active and passive components of the transmitter and receiver or of an amplifier are grown directly in multiple layers onto the substrate, the gallium arsenide substrate, and multiple layers of resistive film metal and dielectric. And they're employed to fabricate the device. Complete radar transmit receive modules are fabricated using MMICs circuits. The low noise amplifiers, power amplifiers, and they use groups of MMIC circuits, phase shifters, receivers, and I'm going to show you an example of just that. Here's a re-rendering of a picture of a hybrid microwave integrated circuit taken from Posar's reference 5, and I redrew it in Adobe Illustrator. Here's the ground plane, a ceramic substrate, and here's a choke which is put on and attached here and here. And here's a chip capacitor. And here's an FET chip, a divider chip, a resistor chip. And here's a hybrid. So we have all sorts of different things we can integrate with microwave integrated circuits, putting pieces on a ceramic substrate with a ground plane. Now, here's an example of a microwave integrated circuit, and it's the power amplifier that's used in the TPS-59. You can see it relative to the engineer or the person's hand that's holding it. And you can see the different strip line technology connecting the different componentry. And transistors or resistors at what level of, like, it's hard to see what level of integration these are. Now here's an example of a microwave integrated circuit where the subsystems are made with MMIX technology. This is, each one of these squares is 4 millimeters by 4 millimeters, and it holds, it is a, the output is 8 watts of power with a 10% duty cycle. As a transmit receive switches here and here. Here are some discrete resistors that are on the system. And each one of these little squares is 4 millimeters by 4 millimeters. And it's an S-band TR module that will operate with in a multifunction phased array radar. And it's got a dual channel for weather and air traffic control. Now when we look at the layout of a typical MMIX circuit, this shows you the kind of integration relative to what I just showed you, and this also is from Posar. We've got, first of all, a ground plane that's metallized on, and then a gallium arsenide substrate, and then we have a metal, an implanted resistor, a gallium arsenide FET amplifier, a thin film resistor. Here's a strip line, input line, a MEMS capacitor, and an inductor. And all made with different substrates on top of the gallium arsenide. Now, when we take just one of the subsystems in that transmit-receive module that macomb developed, and I should say this is a macomb product, what we see is a gallium arsenide. What we see is a dual-channel receiver. One channel here and one channel here. And it's made with gallium arsenide p-hemp technology, and this integrates 2 6-bit phase shifters, 2 4-bit constant phase digital attenuators, 2 low noise amplifiers and switches, all in microwave integrated circuitry inside this transceiver. And each of these other elements also have that same level of integration. Here's the high power amplifier, here and here, the filters, the transmit receive switches, the transmitters. You can see what the transmitter feeds one high power amplifier and then feeds the other one. And then the receiver would come in, and here's the dual channel receiver, a controller. And so you've got a huge amount of integration where this microwave integrated circuit has these different, and the filters, all in a very, very, very small componentry. And now here's an individual TR module, and they are all integrated on the side of a board, and this is the top side, not where the antenna is. I'm going to show you the antenna, it's down below. But this individual TR module is just this little box up here. And this is an 8 by 8 element S-band subarray. And here's the front side of the subarray with 64 patch radiating elements. So you can see the kind of incredibly neat integration that can be done. And here's another example of X-band TR module technology using MMICS technology. And this was also supplied by Macomb. And it's based on gallium arsenide technology. And its main components here are two X-band TR modules. They're a 1/2 inch by 2 inches, each one. And the main components are a phase shifter, attenuator, gain stages, limiter, LNA, the high power amplifier, and silicon pin diode TR switch. And it's a built-in low-cost laminate technology. And you can see yourself the transmission lines down to the different componentry. So that there's a huge amount of progress, as you see in the next section, as we build into it, that we've come to with this technology. Now I'm going to take a break, and then we're going to look at some transmitter receiver architectures which use all this technology that we've looked at, all the way from the higher power transmitters down into the TR module technology at the MMICS level.